Hello and welcome to Algebra 2 with Mr. Clausen. Today we are going to discuss the tangent function, which is going to be the last of the three trigonometric functions that we're going to talk about in this course. And we'll start by relaying some information about how it relates to the unit circle, then we'll talk about how to find some tangent values, and then we'll finish off by graphing a tangent function and seeing how we can do that. So with that said, one of the things I just want to recap with you guys is that when we look at the tangent of x, that's what this line represents, is we see this type of function where it goes, curves around, passes through the origin of a coordinate grid, and goes up like this. And then it starts over, all right? And we see this type of behavior that occurs like this. And then we'll see it one last time here, and it goes through 2 pi, and that's when we'll be done. But one of the things that you should know about a tangent function that we have talked about previously is that a tangent function is equal to the sine, in this case x, over the cosine of x. So it's actually a ratio or a slope between the two. And so if we look at like the tangent of pi over 6, what we're actually doing is we're saying if you're using the unit circle and you're looking at the x and y coordinate, you know that x would be the square root of 3 over 2 and that the y would be 1/2. And so if you want to know what the tangent of pi over 6 is, you would say 1/2 over the square root of 3 over 2. And if you simplify all that out, you know that it's equal to the square root of 3 over 3. All right? And that's what the y value would be at this given point, is the square root of 3 over 3. And we can go and find these particular points of a tangent function. And then once you get past pi over 2, it becomes negative. And the reason that you're going to see the quick switch from the positive to the negative, all right, is because you're crossing this point. And at pi over 2, remember that the value is equal to 0, 1. And the reason that you're seeing these lines here, there's these vertical lines, we refer to these as asymptotes. All right, this is a asymptote. And an asymptote is a imaginary undefined boundary line of a tangent function. And we can explain this again using the sine of x over cosine of x idea by going and saying that the tangent of pi over 2 is equal to 1 over 0. You guys know that this is equal to infinity, so to speak, and that this is undefined. So it creates these vertical boundaries that are present. All right, and so when we're looking at this, we can find some really useful information. Another thing that's worth keeping in mind is that when we have pi over 4, like right here we have about pi over 4. Another thing that's useful to keep in mind is that at pi over 4, you know that at pi over 4, you have the square root of 2 over 2 by the square root of 2 over 2. Those are your x and y coordinates. And with that, if you take the tangent of pi over 4, or 45 degrees, you know that you have the square root of 2 over 2 divided by the square root of 2 over 2, which would simply be equal to 1. And so if you know what this point is here and you trace up, you know, at least for this specific function, because the amplitude is equal to 1, you know that at this given point, if you have the square root of 3 over 3, this is equal to 1. All right, and so that can be useful to keep in mind. Same forward. So with that said, if we want to find tangent values from a graph, if we want to find, a value for y equals a tangent of b theta. So if a is your amplitude, b again is still the number of cycles, but instead of being from 0 to 2 pi, it's just from 0 to pi. So if I go and I look and I go 0 to pi, I notice that there's half of a cycle here, a whole cycle here, and another half of a cycle here. So there's actually 2 complete cycles from 0 to pi here. So I know that b is equal to 2. And this is going to be the value that is super easy to find with any tangent function. All right, the part that's going to be a little bit trickier to find, the amplitude, is going to be something I want to explain real briefly. Your textbook may not reflect on this much, but the thing is that these values are not that hard to find. And how I know that is that if I know from 0 to pi there are two functions, I know that in between from 0 to pi over 2 that there's an asymptote here. And between pi over 2 and pi, there's an asymptote here. It just splits the middle of all this stuff. From pi to 3 pi over 2, there's another asymptote. And from this value to this here, or whole pi, we have another asymptote. And one of the things that you can do is that if you go in between the asymptote and the center of the tangent function, right? You go halfway in between. These are the pi over 4 values of your tangent function. They would represent kind of these in-between points, all right, between each point in the tangent function. And not to be like super sneaky or anything, but if we look at that first quadrant of a unit circle, you know, the point where it equals pi over 4 for a normal function, again, this is where you have the square root of 2 over 2, comma square root of 2 over 2, all right, and if you take the tangent of pi over 4, this is equal to 1. So if you want to know the amplitude of something, you just figure out what pi over 4 is in relation to this function. And so what you need to do is you just need to find that in-between point. I don't even need to go and do anything like, oh, like, you know, pi over 4 equals 2 theta, like we did in the last video, and find that theta is equal to pi over 8. We don't need to do all that, you know, which would be this point right here. This would be pi over 8. We don't even need to do all that. All you need to do, find the point that's in the middle, trace it down, find where it intersects, because what's always happening right in between these points is you have, in this case, tangent of whatever this value is, I'll just say theta, is equal to -1, and tangent of the radian measure of this specific point is equal to +1. So if theta is 2 theta here, all right, what's happening is that whatever this value is representing the amplitude of your function. So in this case, the amplitude is equal to 1. It is super simple to derive and interpret in this specific instance. You don't have to do anything super crazy. It's just in the middle of those 2 points. That is the point where the tangent of whatever function you're looking at is equal to 1 or -1, and find where the amplitude is. All right, so this given function would have a tangent function of y equals 1 tangent of 2 theta. So let's look at a different example. So in this specific case, we have a very similar circumstance. I see that my asymptotes are here again. So from 0 to pi, there is one function. Half of it's here, the other half's there. And then what I'm going to do is, again, I understand that b is equal to 1. So I'm going to go look in the middle of all these guys. So in between the center point and the asymptote, I'm going to go look at all these points and go, all right, where does it go? Oh, 2, -2, 2, -2. If I look at all those points, I can clearly see that a is equal to 2. And so then I would have y is equal to 2 tangent of theta. And I can determine the function pretty quickly, pretty easily in these given examples. All right, so let's do one last example. I want to go over how to sketch some of these. And I did pick a little bit more elaborate example, so please bear with me as I go through this. But I am seeing that the b value is equal to 2. So if I go from 0 to pi and 0 to 2 pi, and I'm being intentional about what I'm picking here because I'm going to go to 2 pi and then I'm going to go to -pi, -2 pi in the other direction. And so the first thing I would actually do to get started here is determine where all my asymptotes are. All right, and for a tangent function, remember, since b is equal to the number of cycles from 0 to pi, the period is equal to pi over b instead of 2 pi over b. All right, so if the b is equal to 2, if b is equal to 2, because I can clearly see that in my function, I know that my period is equal to pi over 2. And this is going to be useful to know. And if I have a b value, I can actually determine where the first asymptote is. In the equation for your asymptotes is as follows. Is negative pi over 2b plus or minus n, which just constitutes as like 0, 1, 2, 3, ... just any whole number, times pi over b. Well, pi over b is your period. This just is simply your period. So if we want to find where the first asymptote is, I'm just going to go negative pi all over 2 times the b value, 2, and this is going to equal to negative pi over 4. So negative pi over 4 is right here. So this is negative pi over 4 right here. And I'm going to identify this as my first asymptote. All right. And now, with this pi over 4, all we have to do is add plus or minus n times pi over 2 to every single one of these, and that's going to be where the next asymptote is going to be. So if we go pi over 2 this way, that would be pi over 4. This is where the next asymptote is. 3 pi over 4. This is where the next asymptote is. The next asymptote. The next asymptote. And we can just keep going over pi over 2 until we have all our asymptotes in place. All right, and I would just label all these out because these are going to be your boundary lines you're not supposed to cross when drawing all these. And so in between each pair of asymptotes, we should have this origin point. And then the other part I want to point out is the amplitude value, a equal to 3. And so what this means is that if we look at, let's just treat this as 1, 2, 3, 4, 5, negative 1, 2, 3, 4, 5 in terms of the relationship here. I know that in between the center point and the asymptote, smack dab in the middle, that halfway where tangent of 2x is equal to 1, right? That would be right in the middle between 0 and pi over 4 or pi over 8 in this given case, like in the other example. That should equal 3. And at negative pi over 8, that should equal negative 3. And then I will just sketch. I will touch the dot. I will go and kind of make it look like a cubic function and come back up. And then I just cycle. And if I know what one tangent looks like, I know what every other tangent looks like, just like with every other periodic function. And I can just go and touch and boom and up. All right. So I'm going to start kind of straight up and down, curve it a little bit, straighten up and down, back up. Start relatively straight, curve in a little bit. I'm going to finish. Okay, and this is a fairly large example, but I'm going curve, touch, go back up. And I know my drawing pad isn't perfect, and I don't necessarily need perfection, but it does help, especially if you kind of plot some of the points like I'm doing, so that if you're doing this for your teacher, they can clearly see that you're demonstrating some understanding of where all these points would be. But this is how you would graph this out. I'm looking at where all the asymptotes are and those type of things, so you know those relationships. So just to recap here, I want to point out that when you're looking at a tangent function, y equals a tangent of b theta, just for your convenience. A, you can think of it as amplitude or magnitude. Both of those are acceptable terms when you're looking at that. B is equal to the number of cycles from 0 to pi. And if you want to know the period of a tangent function, just know that instead of being 2 pi over b, it's just pi over b. And that one cycle for any tangent function will follow negative pi over 2b to pi over 2b. All right. And so I'm just kind of including all these for you so that if you're trying to draw these tangent functions, you have kind of the starting points of where to stop, where to end, and then your asymptotes follow the following formula. You can say pi over 2 times the number of cycles plus or minus n, which can be any integer, pi over b, where n is just equal to 0, 1, 2, 3, bop, 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 bop. It can be any of those values. And so with this information, you can put on your note card or other notes that you're allowed to have, and you can just go and you can start drawing out these tangent functions. So with that said, we recap some relationships of tangent functions with the unit circle. We talked about how to find magnitude and period of a tangent function by looking at a graph, and then we looked at how to do some sketching of tangent functions. So with that said, I hope this video was helpful, and let's do some math.